Imagine a city made entirely of glass. Every street is transparent. Every mailbox is visible. Every letter can be watched as it moves from one place to another. You send a private message through the city, and everyone can see the box it travels in. They can see where it starts, where it goes, and who receives it. The only reason they cannot read the message is because the letter is locked, not with metal, not with a physical key, but with mathematics. In a simple way, this is what the internet is like. Every time you send a message, open a banking app, log into an account, visit a secure website, or make a payment online, invisible mathematics protects what happens underneath. Most of the time, we never notice it. We just see a lock icon in a browser, a payment confirmation, or a message that says "sent." But behind those ordinary moments is a quiet system of trust, and that trust depends on one powerful idea. Some mathematical problems are easy to do in one direction, but extremely hard to reverse. Multiplying two numbers can be easy. Finding the original pieces from the final result can be much harder. Creating a digital signature can be easy for the person with the private key. Faking that signature without the key should be practically impossible. This difference between easy and hard is one of the foundations of modern internet security. But now imagine a new kind of machine appears, not a faster normal computer, not a magic box, not a machine that instantly knows every password, a quantum computer. A normal computer uses bits, and a bit is simple. It can be 0 or 1, off or on, false or true. Every image, message, video, app, and website is ultimately built from enormous patterns of zeros and ones. But a quantum computer uses qubits. A qubit is not just a smaller bit, and it is not simply a bit that is confused. It is described by a quantum state. Before measurement, that state contains probabilities. When we measure it, we only get one classical result, 0 or 1. But before that measurement, quantum states can interfere with each other. Useful possibilities can be strengthened. Unhelpful possibilities can cancel out. This is the strange power of quantum computation. It does not mean a quantum computer tries every answer at once and simply reads the correct one. That is the common myth. The real power is more subtle. A quantum algorithm can shape probability so that certain useful patterns become easier to find. For most everyday tasks, this is not useful. Quantum computers will not make every laptop faster, every game smoother, or every website load instantly. But for certain problems with hidden mathematical structure, they could become powerful in a way classical computers are not, and one of those problems sits very close to the foundation of internet security. To understand why, return to the glass city. You want to send a locked box to someone you have never met. You do not already share a secret key. So how can you lock a message in a way that only the receiver can open? This is where public key cryptography becomes important. Imagine a special safe with two keys. One key is public. Anyone can use it to lock a message, but that public key cannot open the safe again. Only the private key can do that, and the private key stays secret. This idea allows strangers to create trust across the internet. It helps websites prove who they are. It helps browsers establish secure connections. It helps protect payments, software updates, messages, identities, and digital signatures. One famous public key system is RSA. Its security is connected to factoring. Take two very large prime numbers and multiply them together. That direction is easy, but if someone only gives you the final huge number and asks you to find the original primes, the reverse problem becomes extremely hard for classical computers when the numbers are large enough. That difficulty becomes a lock, but a quantum computer changes the map. Not because it breaks every password and not because it destroys all encryption, but because of a specific quantum algorithm called Shor's algorithm. In theory, a sufficiently large and reliable quantum computer running Shor's algorithm could factor large numbers much more efficiently than classical computers. It could also threaten other public key systems based on related mathematical problems. That is why quantum computers matter for encryption. Not all encryption, not every system, but some of the most important locks the internet still uses today. The important phrase is, in theory. The kind of quantum computer needed to threaten modern public key cryptography is not the small, noisy machine we have today. Today's quantum computers are still limited, they are fragile, they make errors, their qubits are difficult to control. A serious attack against modern encryption would require a large, reliable, fault-tolerant quantum computer. That machine does not exist yet at the needed scale. But security is not only about today. Security is also about how long a secret must remain secret. A message that only matters for 1 minute has a different risk than a medical record, a government file, a business contract, or identity data that may still matter 20 years from now. This is where the quiet danger appears. An attacker may not need to decrypt something today. They may only need to copy it today, store it, wait, and decrypt it later when stronger quantum computers exist. This idea is often called harvest now, decrypt later. It means the attack can begin before the final decryption is technically possible. The data is collected now, the damage arrives later. That is why the quantum threat is unusual. It reaches backward. A future machine could make present-day captured secrets vulnerable. This does not mean everyone should panic. It does not mean every personal account is already broken. It does not mean the internet will suddenly collapse tomorrow. But it does mean governments, banks, hospitals, cloud providers, infrastructure companies, and anyone protecting long-term secrets have to prepare early. Replacing cryptography across the internet is not like changing a password. It is more like replacing every lock in a global city while the city is still awake. Browsers have to change, servers have to change, certificates have to change, messaging apps have to change, payment systems have to change, software libraries have to change, old devices have to change. And some systems are hidden so deeply inside companies and infrastructure that even finding them is difficult. That is why the answer to quantum computers is not panic. The answer is preparation. This preparation is called post-quantum cryptography. The name can be confusing. Post-quantum cryptography does not mean encryption that runs on quantum computers. It means cryptography designed to resist attacks from both classical computers and future quantum computers. It runs on ordinary computers, normal servers, normal browsers, normal phones, and normal software. The difference is the mathematics underneath. Instead of relying on problems like factoring large numbers or solving certain elliptic curve problems, post-quantum systems use other mathematical structures that are believed to remain difficult even for powerful quantum computers. Some approaches are based on lattices, others are based on hash functions, error-correcting codes, or different hard mathematical problems. You can imagine it as building new locks before the old locks become weak. The door is still the same, the house is still the same, the city is still the same. But the mechanism inside the lock changes. Because the internet is enormous, this cannot happen instantly. There will be a long transition. For a while, old and new cryptography may exist side by side. Some systems may use hybrid approaches, combining traditional methods with post-quantum methods, so that security does not depend on only one assumption. This transition sounds boring, but boring is exactly what we want. The best future is not dramatic. No global blackout, no sudden end of privacy, no mourning when every secure website fails. The best future is quiet. A browser updates, a server changes its key exchange, a bank replaces certificates, a cloud provider tests new algorithms, an operating system adds support, a messaging app migrates, users see almost nothing. The lock icon still looks the same, the website still loads, the payment still works, the message still sends. But underneath the ordinary experience, the mathematics has changed. That is what successful security often looks like. When it works, nothing spectacular happens. The secret remains secret. The connection remains trusted. The identity is verified. The world continues. And there is another side to the story. Quantum computers are not only a threat to old encryption, they may also become scientific tools. Because nature itself is quantum mechanical, quantum computers may one day help simulate molecules, materials, and chemical reactions in ways that are extremely difficult for classical computers. That could matter for batteries, medicines, fertilizers, solar cells, superconductors, and materials we do not know how to design yet. So, quantum computing is not simply a code-breaking story. It is a story with two sides. On one side, it could challenge some of the digital locks we trust today. On the other side, it could help us understand the physical world more deeply. The danger and the promise come from, still, it is important to stay honest. Quantum computers are not magic. They are not finished superweapons. They are not useless hype either. They are difficult machines built around fragile quantum states. A qubit can be disturbed by heat, vibration, electromagnetic noise, imperfect control, or tiny interactions with the environment. This problem is called decoherence. When decoherence happens, the useful quantum information begins to disappear. The wave of possibilities becomes harder to control. The carefully shaped interference breaks down and the computation may produce the wrong result. That is why error correction is so important. In a normal computer, a bit can be copied, checked, and corrected. But quantum information is different. You cannot simply copy an unknown quantum state perfectly, and you cannot constantly look at a qubit without disturbing the state you are trying to protect. Quantum error correction has to detect and repair errors without directly destroying the information. That is incredibly hard. It often requires many imperfect physical qubits to create one more reliable logical qubit. This is why headlines about the number of qubits can be misleading. A machine with more qubits is not automatically a machine that can break modern encryption. Quality matters, error rates matter, stability matters. How long the qubits remain coherent matters. How accurately gates can be performed matters. How well errors can be corrected matters. A cryptographically relevant quantum computer would need reliability at a scale far beyond today's noisy devices. So the timeline is uncertain. Nobody can honestly give a perfect year when the threat becomes practical. Some problems may turn out harder than expected. Other breakthroughs may arrive faster than expected. That uncertainty is exactly why preparation matters. Waiting for perfect certainty would be dangerous, but panicking as if the danger has already arrived would also be wrong. The calm answer is this: quantum computers could break some old public key systems if those systems are not replaced in time, but the internet can adapt. Cryptography has changed before. Weak protocols have been removed. Old algorithms have been retired. Certificates have been updated. Browsers and servers have migrated to stronger systems. Security is not a finished object. It is a process of repair, replacement, and adaptation. The quantum transition is another chapter in that process. For ordinary people, the lesson is not fear. Most users do not need to personally choose post-quantum algorithms. They will not wake up and manually replace RSA with a lattice-based key exchange. The transition will mostly happen inside the tools they already use: browsers, apps, operating systems, banks, cloud platforms, and messaging services. But ordinary security habits will still matter. Strong passwords still matter. Password managers still matter. Multi-factor authentication still matters. Software updates still matter. Not reusing passwords still matters. Phishing will still be dangerous. Fake login pages will still be dangerous. Misconfigured systems will still be dangerous. Quantum computers do not erase the basic rules of digital safety. In many cases, the easiest attacks are not futuristic at all. They are ordinary human mistakes. That is why security has to be layered. Encryption is one layer. Authentication is another. Software updates are another. Device security is another. Backups, identity checks, safe communication habits, and careful infrastructure all matter. A quantum-safe algorithm is powerful, but it is not a magic shield around a careless system. Real security is built from many protections working together. For organizations, the message is more urgent. They need to know where cryptography lives inside their systems. Which protocols are active? Which certificates use vulnerable algorithms? Which devices can be updated? Which systems protect data that must remain secret for years? Which old machines are still running forgotten software? These questions sound boring, but they are the beginning of serious security. You cannot replace a lock if you do not know where the lock is. and that is the deeper lesson of the quantum age. The internet is not safe because nothing ever changes. It is safe because people keep changing it before old assumptions fail. A city survives because its bridges are inspected, its roads repaired, its defenses strengthened, and its weak points found before disaster arrives. The internet is similar. It is a living city of protocols, devices, servers, keys, certificates, apps, companies, and users. Some parts are modern and maintained, others are old, quiet, and forgotten. The quantum transition has to reach both. So when we ask whether quantum computers will break the internet, the most accurate answer is not yes, and it is not no. The better answer is this: they could break some of the old locks. The internet still depends on, if we leave those, locks in place for too long. But if we prepare early enough, the internet does not have to break, it can transform. The mathematics underneath can change while the human experience remains familiar. Messages can still be private, payments can still be secure, identities can still be verified. Trust can survive, but only if it is rebuilt before it is tested. Quantum computers are not magic. Encryption is not permanent. The internet is not unbreakable, but humans are not helpless either. We can study the threat, build better tools, replace old locks, and adapt before the future arrives. Somewhere right now, old mathematics is still protecting our digital lives, and somewhere else, new mathematics is being built to protect what comes next.